This is a giant Minnesota quartz vein. And you know what they say, where there's quartz, there's gold. Not really. But we're going to explain some of the geology and look at this vein today. Now this is a pretty significant quartz vein. It's pretty wide, pretty substantial, and it's right next to the Thompson Dam, which is right next to Jay Cooke State Park. Now you can see the road behind me is actually built into this quartz vein. And I can guarantee one thing, if there was gold in this vein would have been gone a long time ago. Just because there's a quartz vein doesn't mean there's gold, because the right conditions have to be met. Now, cutting through here is the St. Louis River. It's a massive river in Minnesota, and in this part, man, it is some rough water going through all these rocks. But this vein, you can see it cuts through here, and then along the side, there's all these smaller stringer veins that go off like so. Now if I follow the vein down, it stays pretty significant until about here. And then you can kind of see it getting thinner and thinner and pinching out. And on this end, before it gets to the river, it's only, 3 feet wide, maybe a little bit more than that, and it's kind of ratty a little bit. And if we look to the other side, we can't see that quartz vein at all. Now typically a quartz vein is going to deposit where there's some kind of structure, like a fault. Now I don't see any obvious change between the rock on one side versus the other, but that doesn't mean there's not a structure here. Obviously there's room for the quartz to grow and a conduit for fluids to flow in. Now the surrounding rock is a lot of slate. Slate is a metamorphic rock, and that means there was a mountain building event. The mountain building event that caused this would have been the Pinokian orogeny. And that runs from Minnesota all the way through Wisconsin up into the UP. When two tectonic plates collide, it causes upheaval and buckling, and you get your mountain building event. Now, mountain building events are a great place to look for gold. The technical term for mountain building is an orogeny. And the gold deposits they find within are orogenic gold deposits, and they're a very common source of gold. They'll find the gold in a quartz vein, but in order for there to be gold in the quartz vein, the right conditions have to be met. When you have all these tectonic forces, it generates a lot of heat and pressure. That can cause dewatering of the rock. And there's different ways dewatering can happen. You can have water trapped in the rock, and this is all sedimentary rock, so there's probably a lot of water that was trapped in there that got squeezed out during the metamorphic process. But also water can be contained in minerals themselves. And as you heat them or pressurize them, that OH molecule can be released in the form of water. Anyway, when you have this dewatering, you have a lot of fluids present. Now you get hot hydrothermal fluids that are flowing through the rocks, flowing through the faults. They can deposit quartz veins like this. And along that journey, they can pick up minerals like silica and gold and silver or copper or whatever. But there isn't necessarily a lot of those minerals present everywhere. Furthermore, gold doesn't necessarily like to be in solution, so you have to have a ligand present. Commonly, that ligand is a sulfur-based molecule that helps drive that gold into solution. But the real science behind all that would be for an economic geologist or a geochemist. Now, as the fluids are going up through the conduit, whether it be a fault, a shear zone, or whatever the structure is, it's changing pressure and temperature. And as it goes up there cooling, you can hit precipitation points. Every element will have a different state of solubility, and if it's not in that happy window, it will start to solidify and precipitate. Now right here is a very small trace amount of oxides. And typically you'll see that when a sulfide mineral is deposited and starts to weather away. That classic rusty color is a telltale sign that there was an oxide in there that's weathered away. There was likely a sulfide nodule in there, now it's a spider house, and there's that oxidation from the residual sulfides. You see a little bit of that here, there's a little bit more down here, right there. But for the most part, this quartz vein is pretty clear white. So why is there no gold in this quartz vein? I don't know that there's no gold in this quartz vein. There might be a trace, but it's obviously not economical because this is such easy pickings it surely would have been mined. So we're gonna go ahead and say there's no gold here. Why is there no gold here? Well, in this part of Minnesota, we're on the edge of the Pinokian orogeny. So one reason I would hypothesize is that this is gonna be a shallower, cooler part for these hydrothermal fluids, which means it's potentially possible that any gold-bearing mineralization would have deposited far deeper or far more interior to the mountain building events. This would have been on the fridge where all the elements have long since been scrubbed out by that precipitation process. That's one possibility. Another possibility, there just wasn't a ligand present to drive the gold in. Another possibility, there was no gold to begin with. Maybe the fluids just didn't run by a gold-bearing geologic unit, so there was never a chance for it of being gold-bearing. I'm not really sure. That takes some heavy-duty science to figure that out. But most quartz veins that you find are not going to have gold in them. Gold-bearing quartz veins are a rarity. Gold is rare. However, maybe we'll take a chunk home and crush it up just for the fun of it and see what we find. That doesn't mean there's not gold in the St. Louis River, however. There could be, and that would have come from the glaciers. And since I'm the glacial gold hunter, that's what we're gonna hunt for today. However, you can't pan in the state park, so don't do it. But we'll take a field trip anyway. Now this channel here is full of water during like spring runoff, high water events, and it's just stacked piles of boulders and gravels up here, and it gives us a good window of what type of rocks are in the area. And of course we've got a lot of pieces of slate because that's the bedrock around us, and some metasedimentary rock, which again is the rock around us. Slate and greywacke. Greywacke is like a dirty sandstone. Instead of pure quartz sand, it's got a lot of other stuff mixed in there. Call it greywacke. But in addition to that, I see granites, I see gabbros, I see basalt, I see gneiss. Now gneiss is a metamorphic rock, and that's what I'm looking for primarily. The Pinokian orogeny isn't known for depositing gold, but the Algoman orogeny up in northern Minnesota and into Canada, that was a gold generating mountain building event. So if the glaciers scraped over the gold fields and deposited any till here, that would be the source of the gold we're finding. Not from the Pinokian orogeny, but from the Algoman orogeny or Kenoran orogeny far north at the Canadian border. So these other random pieces tell me that the glaciers did deposit some material here. However, I'm seeing a very minimal amount of metamorphic material, and specifically greenstone. The greenstone deposits are what generate the gold in the Algoman and Kenoran orogenies. So typically I tend to do better when I see a more metamorphics when I'm panning, but you never know until you dig a hole. However, we're still in the park, so no digging yet. Let's keep exploring. Look at all those phenocrysts. Square prisms of plagioclase feldspar. So cool. I love these rocks. Now, Jay Cooke State Park is basically the Grand Canyon of Minnesota. This river has carved this huge canyon into the bedrock, and you're seeing the inside of the Pinokian Mountains, the edge of the mountains anyway. Right here, you can see what we call an anticline. You see all the bedding planes have been bent up and warped, and that's from that tectonic stresses squishing it together and warping and bending the sediments. If it bends up, it's an anticline. If it bends down, it's a syncline. And you'll see this accordion type structure all throughout the rocks here. Super cool. There's a squirrel. Now slate is known for having a perfect cleavage plane. I actually might be able to break this one in half. Oh boy. And I cut myself. It's ridiculously sharp too, like that. But slate is a low scale metamorphic rock. The protolith of slate, and protolith is a word meaning what it's derived from. Every type of metamorphic rock comes from a different type, a different source, and that source that it comes from is called a protolith. So the protolith of slate would have been shale, basically a mudstone, claystone. And as it undergoes the pressure of the metamorphism, it gets these perfect cleavage planes. And it sounds very different than shale. It's like a sharp, almost a ring to it, where shale is more of a dull thud. As it undergoes that metamorphism, the mineral structures start to change. It starts to grow new minerals, and it starts out as a slate, and then as it undergoes more, it becomes a phyllite. Beyond that, it becomes a schist. Beyond that, it becomes a gneiss or a, what is the word?
Migmatite.
And beyond that, it starts to melt again and turn into a different type of igneous rock. And right here, you have another interesting feature. It's a basaltic dike. There was a fracture here, and it was forced open by this molten magma. Now, it looks very similar to the slate. The only difference that you can really see by eye is a slight textural difference, and there's no cleavage plane in this. You can see right here, you got that perfect cleavage, and then as soon as you cross this boundary, you can visibly see the boundary, there's no perfect cleavage plane. There is some jointing, and they call that columnar jointing. That's characteristic of basalt. And that pattern you see on Devil's Tower, that's all columnar jointing. Same thing you're seeing right here. But the color and the texture are really kind of similar. And if you grabbed a piece of this and said, what kind of rock is it? It'd be a little tricky to figure that out. I'd have to really see something definitive to tell me what it was. But here in the whole setting, it's pretty easy to pick that out, and that's a really cool feature. Geology's cool, but that's about all we can do in the state park. Now let's go see if we can find any of the surrounding creeks that we can actually prospect in. So we are outside of the park, far upstream, and I think this is a place of public land that's okay to dig. So I'm gonna dig right in this boulder field here. Now in and amongst the boulders are all these cobbles and gravels, so that looks good, like a good depositional environment. The thing is, I'm only seeing one type of rock. I see gabbro. Every rock around here is gabbro. Now gold isn't gonna come from the gabbro. It's gonna come from those metamorphic rocks, those orogenic deposits. But the only way to know for sure is to dig and pan it out. Maybe I'll reveal some other glacial deposits when I dig in here. See what I see here. Ideally, I want to see a good mix of glacial deposits. And there's pieces of granite and pieces of sandstone. You never know what's there until you pan it down. You just hope the glacier's passed over the gold fields and dropped a little bit of that off right here, or within reach of the river anyway. So a little bit of black sand, but let's see if there's any gold with it. Nothing. Well, one pan is only enough to tell if there is gold there, but it's not enough to tell if there isn't gold there. So I'm going to take a few more pans here and there, and I'll let you know what I find. Well, I've been taking test pans here and there, and I can't find a single speck of gold. Now, I don't know why glaciers drop off gold in some places and not in others, but they just do. And as far as I can tell, the glaciers didn't drop any gold specks here, nor did the river wash any this way. Not that I can find. So we'll head to another spot and give that a try. And our next spot is a giant gravel pit. Now this particular pit is on an esker, and an esker forms underneath the glacier. It's basically a river that flows underneath the glacier with the walls of the glacier on each side of the underground river, or under ice river. So in the end, you're left with this ridge, this little windy ridge of gravel deposits. These are great places to put gravel pits, and they're also great places to look for gold. You can see right here all this stratification of the deposit. This was sand flowing at the bottom of the river underneath that glacier, and you can see it just deposited in all this strata, the stratigraphy. This would have been like a big sandbar. But then we look up a little bit and we see big deposits of cobbles. And what's happening is as the river's flowing, it's kind of meandering, and it'll deposit like an inside bend of sand, and then it'll build and then deposit more material over it, and it kind of layers with like sand or cobbles depending on how that river is meandering. If you follow the sand up there, you see right there is a boundary of all those cobbles. You can see that's actually a river channel, and it looks like it happened several times. It goes from sand to cobbles, back to sand to cobbles, and then back to sand again. Technically speaking, this would not be glacial till. Till is unsorted. It's that bulldozer pile that goes through at the end of the glacier. But since this is stratified and actually sorted a little bit, that's not technically till. It's still glacial deposits. It came from the glaciers, but this would be more of an alluvial deposit. So there's a little bit of distinction in the glacial features that we see. That's just words though. It's glacial deposit, and there might be gold in there, so let's test it. Quite often these gravel pits will have little ponds in here just for panning. Should have put my mud boots on. Oh, I hope there's some gold in this pit. This is a nice one. Nuts. Nothing. Dang it. Well, after a little more panning, no sign of gold. I seem to be striking out today. Now it's good glacial material. I'm seeing a lot of igneous rocks, but again, very few metamorphics. When I pan it down, I'm not seeing any garnets either. Garnets are a metamorphic mineral, and typically where I find gold, I find a lot of garnets, I find a lot of metamorphics. So far in my observation, I seem to do best when I find those metamorphics. I mean, there could be differences in other parts of the state, but my working hypothesis seems to be that there's more gold specks associated with those metamorphics. But I haven't been everywhere, so maybe I'll be proven wrong. Maybe you can prove me wrong. Anyway, I'm not finding any gold here, but we still got some rock to crush up. So let's do a quick crush and see if we do have any trace of gold for the day. All right, so we're back home, and I took just a few small samples back home, and we'll give these a crush and a quick pan. You can see with some of these samples, I did capture some of the sulfide staining, and I figured that'll have some of the best chances of having any presence of gold at all. And then some pure white quartz that looks like something was weathered out of it. And I brought this rock home, which is just a hint of quartz, but there's a lot of oxidation. So a lot of what I think is sulfide staining. So we'll just crush all this up, pan it out, and see if there's any specks of gold. So I crush that up, and once it gets about this point, it's really hard to get it to go any farther. But I got a good bit here, and I think that's enough for a sample. So let's pan that out. So I just got a tub here, and we'll just pan it out quick. And it turned all brown. You never know what color it's gonna turn. Sometimes it's brown, sometimes it's like milky, sometimes it's rusty red. This one's brown. So there's a whole bunch of shiny stuff in there. I think there's a fair bit of metal from my stamp mill I made. Little shards of steel, it looks like. Let me get a magnet. Look at that. All kinds of little metal pieces in there. It could be a mix of pieces of like magnetite, and it could be a mix of metal shavings from my little stamp mill. And that's what we got left. Some silvery sparkly pieces, but I don't see any golden pieces. So I would guess that most of those are just pieces of sulfides. That one there's a little golden maybe, but sulfides are golden too. So, well, I look through that and I see some shine, but I think it's all just sulfides. There's one tiny microdot that does have a little golden color, and it moves a little different. You know, you gotta get a feel for how gold moves in the pan. It's possibly a little microdot of gold, but it's so small it's really too much to tell. If I really wanted to know if there was a trace, I would take a sample of that and have it professionally assayed. So no gold today, but today was more of a geology field trip anyway. I lean heavy on the geology lesson when there's not a lot of gold to be found. I hope that's okay. Thank you guys for coming along. Come on back for the next one. Bye-bye. What am I doing wearing this?